Hi, I'm Matt from OpenGov, as you just saw. And we're going to talk kind of into a realm of data science that I did early at OpenGov, and we're renewing kind of actively at the time. So I want to open a little bit with kind of what is OpenGov if you missed the talk right before us. So we are a software as a service company that provides financial data management, visualization, and collaboration for governments in the 21st century. This is kind of something where governments have been behind the kind of tech industry. They're oftentimes stuck kind of in the 80s or 70s in terms of technology, so they haven't had the help that a lot of other companies and private sector has had in collaboration to build up better and better tools. So we're trying to solve that problem, and we're also trying to solve the problem of connecting like governments themselves, connecting governments within their own organization to other governments and to their citizens. Currently, we're just over 1,000 governments, depending on how you count them, in the US and a couple in Canada, and we've been around for about 4 years. I joined in the first couple months of the company and been here ever since. So today we're going to kind of outline a challenge that I hit when I joined OpenGov, and that is still persistent, and I've seen colleagues of mine also hit, where you want to use traditional techniques you've learned, you want to apply data science to get some value out of your data from your customers, but that sometimes that's very challenging in new market spaces. In some places, there's no repository online for you to look up. There's no relationships already established that you can use in your data. And training data, especially in niche markets, can be really difficult because you need domain expertise to even generate it in the first place. And it becomes a really large challenge for supervised learning. So today we're going to walk through a few of those difficulties and some processes we use internally to kind of get our foot in the door in that space. So I talked about problems with these very specialized spaces. Government records in particular are a great example of this. There is tons of government records online. They're not organized, nor are they well classified except at a very high level. And that really leads to, if you want to do valuable insights out of data, it's hard to mine that out of the public records that are available. And on top of that, there's very few knowledge bases to leverage off of. The existing ones like WordNet and DBpedias, all these other sources, they're rather sparse in our domain. They have the high level terms and where they came from, and that's about it. So the other problem we have is as a young company, our data grows very fast. It almost consistently since day one, it doubles every 6 months. It just keeps doubling every 6 months, which is a challenge in itself. I already covered the knowledge base is limited. Training data is also sparse. I tried building some for ourselves. It got outdated very quickly. And so that is a hard thing to establish well, especially as you change the type of things you're asking about your data. So as I talked about our data growth here, you can see this is the curve of one of our label tables that just keeps growing. So this is all of our labels as they've gone up, and you can see the training data that I put in 2013 didn't really cover very much of the space now. And this is going to continue to happen. So we really have to kind of garner some insights without having lots of training data. That doesn't mean that we won't use training data. Like semi-supervised is a great step from unsupervised. But we have to start somewhere. So when you're exploring textual data or unstructured documents, you don't know many things, especially if it's a new realm. You don't know kind of how many topics there are, how many precise classes, and you can run into this problem a lot when you're trying to discover an ontology like we do, social trends and markets. You don't know how to kind of bucket things to even ask the question of, is this A or B? You don't know what A, B, or C, or if there's Z. There's a couple families of unsupervised techniques. One of the traditional AI approaches to unsupervised is to sort of define a utility function and let a program explore a space where you reward it for doing well. And you try to define what well is, and you try to define the space, and you hope it tells you something useful. And you can learn optimal paths through that space. You can learn about what's some end result that you can reach. But it is kind of, you have to have a lot of engineering effort, a lot of knowledge put into that algorithm to set up the space in an easy to explore way. The other alternative to the kind of utility optimization is clustering. So clustering relies instead on having very enriched data, is that it relies on associating data in state spaces relative to other data that you found. So if you just have lots and lots of data and it's growing exponentially, it's perfect for clustering, other than the fact that clustering goes a little slow as you get too much data. But it does tell you it answers many of the questions about what's in this data, what's the big pictures. As you get more data, those pictures get clear. So there's like a huge swath of family of clustering algorithms. There's centroid based. If you implement k-means, I think in school back in the day, I implemented k-means in like every single class. It was at least 8 times. But there's some more interesting ones you run into. Like there's EM, where you're trying to do probability distribution, maximization, minimization, and then there's hierarchical as agglomerative clustering. And these are just 3 classes. There's many more. And they kind of arrive in sort of 2 major flavors. There's sort of bottom-up and top-down clustering approaches. The top-down approaches look at, I have all the data in one cluster, how do I break it up into smaller things until I get to a number of clusters I like? The bottom-up approach, alternatively, is really looking at, pretend everything is its own cluster, and then try and group things that seem to have relationships that matter into larger clusters. So of that former group is hierarchical agglomerative clustering, which is a mouthful. In this method, it basically does a bottom up, it groups things together, and it scores each possible grouping as you group different clusters together until you have all possible groupings from nothing group to everything in one cluster. And there's a particular, the original author of that algorithm, one of the 2 authors in that algorithm came up with a greedy version of this method, which actually has really nice performance characteristics, and it solves a lot of the problems that are in sort of unsupervised techniques, at least for data exploration purposes. You get, it's resistant to missing data, so if you don't have all your edges, it's okay because the friend of your friend becomes your friend in a clustering algorithm. So if you have chains of relationships, as long as you can get there somehow, you'll oftentimes group together even if you don't directly relate. And you don't need no starting state, you don't need how many clusters, you don't need a starting centroid, you can just run it on data and not have to parameter tune very heavily. And so what does this clustering kind of look like? So here we have some labels where I've kind of colored in ranging from red to green how much this thing is like that thing according to some algorithm. And in this case, this would be common something where you've gathered a bunch of data and you said, I've got sentences A through Z and I need to know which ones relate to what. And these are just some arrows where we say these are the relationships, we put them in a graph. If we don't know k-means, like we can kind of see it visually that there's 3 groups here, but if k-means, you'd have to tell it or do sort of a k-optimization algorithm on top of clustering, which gets complicated. Hierarchical clustering just will give you a nice group of clusters, and unfortunately you can't see it on the screen because of the resolution, but we have 3 groups, one around the law enforcement, one around sewage and water, and then one around the street cleaning and street sweeping. And it will solve and find those and then give you this, which is a dendrogram. And what it says is it'll do is pretend the data you just saw was in this dendrogram. It would go and slice at what point is the quality of each of those clusters highest. And in this case, it kind of sliced right across the graph at something around the 0.6 range of the y-axis scale. And so then each of the color groups is a different cluster of terms or objects that you've put in this graph. This also lets you say, it can tell you what the best choice is, but you can override it too. If you're really looking for 3 things and you have 3 things, ask for what the 3 things are. You can just slice that dendrogram at a point where you have 3 clusters. And so it has a lot of capabilities to sort of tune and parameterize, especially if the quality score doesn't quite match your expectation, you can tune it up or down some. All right, so today we're going to be doing some live coding, and we're going to go dig into this site called GovRank, which United States Common Sense recently just launched this year, and it has a huge collaboration of budget and audit PDFs from governments across the US. So it's a really nice centralized source to kind of find some information in our domain that we're working in. We've done this effort in the past on our own, and they have a better repository than we do. But what's in these files? We don't really know, so how about we have a machine learn it? But first we're gonna go pop over and look at what some of these look like. So the GovRank site here, you can search and I can walk through. So if I look for San Francisco, I can pop in there and I can find all the data that San Francisco has published each year. assuming that our internet works. Well, I can show you instead what I actually downloaded, which works just as well. Now, there we go. Yeah, it just took a second. So here's San Francisco. Here's all their audits and budgets, all the way up to 2016. You can download these, kind of look at what the content is. So I have some of those downloaded already. Here's the one, we saw if you were here for a prior talk, we talked about Addison, Texas's data structure. This is what their budget PDF looks like. They range from like pretty pictures and nice graphs to like a giant blob of text that is a picture of an image that put into a PDF. This one's a little bit nicer than many of them. And so it has a lot of there's some topics in here. You can see there's some chapter heads and they talk about kind of what the budget document's about. This is a really big document. It's 156 pages. This is kind of average size. They build this every year. And it has a lot of information in it. To read through this, if you want to read through 1,000 of these and find information, that's a pretty hefty task. So let's not do that, and let's have a machine try and tell us what might be in here. All right. So we're going to do a little IPython shell here to kind of explore some of that data. So, yes. What's that? GitHub is, I did not post on GitHub, but I did attach it to the talk. So the code is attached to the talk along with the data I used. Here we basically have, I put a few utility functions here. We have read the data, and then we're going to use this progress thing so we can see how slow or fast something's going later. Here's a few sources. I downloaded about 10 budget PDFs, a size enough that you can get some intuition out of, but not so much that we are going to be, taking forever during a talk to process it. All right, so kind of what's in these texts, right? So if we want to see what, what's in, let's say, Sunnyvale, we can take this, grab the text we loaded from Sunnyvale. Let's look at maybe the first 5 sentences. Or actually, from here we're going to look at the first, let's say, 100 characters. So, we can see, great, there's some City of Sunnyvale, director of city officials, so on and so forth. Maybe what's, our last 100 characters. This file's really big. So last 100 characters actually takes a little while to get to.
So, and when you pulled the text from the PDFs, you didn't do any cleaning step at all? You just relied on the tool?
Correct. I use PDF to text. The PDF to text, and actually it's okay. If you have a question in the middle of this, is really confusing, it's fine to pop up with a quick question. I may ignore it if I'm out short on time. Yes, this is just a PDF to text. It's just a standard text extractor. It does, however, not keep the nice structure you see in a PDF. Sometimes the text just ends up on new columns, even though it's part of the same logical group or part of a different group on different columns. So we'll talk about this later. It's going to cause a little bit of an issue. But for now, we have this data that we've collected up. All right, so first, let's get some NLTK. If you haven't used NLTK, it's kind of the backbone-based library you want to start with when you do things, but it's not perfect. So here we're going to have a few, I'm going to grab my notes for this because the loaders for all the different types of things can be a bit dense. So first we need to find sentences in this data. We're going to extract sentences. We're going to try and find a sentence which tells us something about the data. So let's grab nltk.data.load. And we're going to load a tokenizer that comes with NLTK called Punkt. It actually doesn't do great on PDFs, but it does better than the other ones. But that's okay because we just kind of want to do some exploration, and then we'll come back and we can say where we could do this better if we have more time. So we've got this, we also want to tokenize our sentences. So we're going to make this tokenizer here, which we're just going to split on kind of new lines, or actually any white space, to get our words that we want out of this. Great, and then we have, we don't want to, we definitely want to prevent things like stop words from messing up our results, which they definitely do if you don't take care. So stop words in this case, if you're not familiar with them, are words that are very common in the language and generally don't carry a lot of semantic meaning. They mostly are structural to the sentence. And in this case, we're just looking at sets of words, bag of words, so we don't really care about the stop words. And so these are also techniques you can just kind of pull in. These kind of come for free with NLTK. You can make better lists, especially if you have domain knowledge. You can add domain stop words, which we use a lot. And then we're going to make a little stemmer here, because if we just look at the words themselves, you'll find that they oftentimes have random characters in them, or are capitalized in weird schemes, or have adjective or verb forms that we don't care as much about as the kind of subject matter.
You have a small typo at the end of your stop word line. Spelling for English.
Oh, yes, thank you. I swear it's my native language.
I think it's also spelled quarter.
Yes. So this is the problem with trying to talk and type at the same time. Thank you guys. You guys are my proofreaders, my code reviewers as I go here. The later parts are a little easier to type because they don't have this deep semantics. So I'm just going to make a little helper here. And also in a second, this thing will tell me if I messed up. So that's because I can't spell. Great. All right, so we now have a bunch of tools from NLTK. We've imported them. Now let's actually use them. So here. All right, so the first thing we kind of want to do is let's generate some sentences. So we're going to use this name tuple, which is a form in Python to sort of keep track of list-like objects, but with a name. So we're going to make this sentence name tuple. And we're going to add a few attributes here so we can keep track of it. We're going to do original. So we're going to get the raw text in there. We're going to pass in tokens. So we're going to make some tokens with our stemmer that we can compare with that are more sensible. And then we're also going to list the source, like where did this sentence come from, because otherwise it's sometimes hard to tell if you have a bunch of data from the same point or from different points. And then we're going to make a little tokenizer.
You make it sound so easy.
Well, I went through this talk several times on my own, so that made it a little bit easier to talk about it. So what we're going to do is, here first, we're going to start with some for loops. I'm going to kind of manipulate this as we go. So we're going to say for word in our extract words. So we're going to extract some words from some sentence object that we get. Now we need a sentence to actually process to work on this. So we're going to say this is going to be well, okay, sorry, I forgot. Yes, we already have a sentence coming in because it's an argument. So some things we want to do here, like we have the sentence, we can say just W, which would be just the word by itself, but that's not very helpful because, as we said before, there's lots of ways to represent this. We could do dot lower, and that helps a little bit. Now like capitalization won't mess with us, but the reality is that we probably want something more sophisticated, and this is a good first step. So we're going to stem this, and I'll show what these look like in a second. So the stem is going to take that word is going to kind of compact it down to just a few characters that kind of are only the consonant values, not exactly, but effectively.
Don't filter diacritics.
Well, we're gonna do a little bit of filtering here because otherwise this still won't help because you get a lot of token size 1, token size really big. So first thing we're going to do is we don't want stop words, right? We said we didn't want those. Great, now we don't have stop words. What else don't we want? We probably don't want to pull in anything that doesn't really. So when I print out these text files, you're going to see there's a lot of random characters in the PDFs. So what we really want to do is we kind of want to skip any words that really aren't words. So we're going to do, we're going to match the text that we're actually getting in here. And we're going to say, let's only grab things that kind of have, sort of A through Z type operators on it. This means that we're only going to get text. If we get something that has other things besides text, let's skip it. Yes, so, and ideally, we might be losing some information there. But for now, we want to just explore the text. If we want to do something else, we'll do it. And then I'm going to do this little step, because if I don't do this, the data won't look all that great. As experimentally discovered. So this will cut out the stems of length 1 and 0, which some of the words get split by individual characters. Can I make the screen bigger? Does that look better? Great. All right, so this, now we have a tokenizer, so we can tokenize a sentence. So we actually want to, let's actually make those sentences. So we're going to do for source and text in the text that we pulled up above. So up here, we're going to have text items. And in here, we're going to, let's grab the, the original sentences. So, so we're going to grab that text, we're going to grab some original sentences, and then we're going to get some tokens. So tokens. We're just going to take that tokenizer function we made, we're going to map it in. And we're going to use these O-cents. So this will convert each sentence into tokens. And then we're going to make an actual sentence object. And actually, because we have to map this data in, we're going to do a little bit more to form this. I tried to make this a little bit cleaner, but bear with me. We'll just kind of get through the how to build this nicely. And we're just going to zip these things together. I'm using a lot of different Python built-ins to kind of go quickly through this. But if you're curious any of these, that code will be online, so you can quickly look through it. All right, so, and let's p-print sentences, maybe the first 3. I probably have a typo. Oh, we need to append, so. Oh, and we should also probably further filter these sentences a little bit more. All right, and I still have enough minutes, I think, to get through this. So we have this. We're going to take the so lambda, we want filter that. My Ruby development is rubbing off on me. No, Ruby has its uses. Name tuple is not defined because I can't type. This is the problem with live coding. The worst case, I'll just copy over the working example and we can move forward. Yeah, and actually, for the sake of just speeding this up because we are running out of time, I'm going to go cheat. Oh, look at this, magic code. Yeah, but we went through it, and let's get that, of which apparently I typoed in copying. All right, it's because I called extract sentences the wrong thing. And tokenized sentence. Stop words is not defined. Okay, so that should work. Thank you. PP, let's look at this now.
You're modifying the cell while it's running.
Well, I'm iterating over one thing and modifying the other, so it should be okay. Some of these sentences are pretty beefy. So here we go. Here's our sentences. You can see here we have City of Sausalito, strategic resource. And down here we have our tokens. So here's our different tokens that we're going to use to compare. And this source comes from budget Sausalito. So this is our Sausalito data. We've broken it into tokens. We've kind of grouped it all up together. And now let's actually kind of do something useful. Also, I parsed all of those PDFs. So now we have this for every single sentence in every PDF. This is about, I think, 40 or 50,000 sentences before we filtered. All right, so next thing we're going to need is Jacquard. We need a little function called Jacquard similarity. And for the sake of time, I am going to just copy this over. I'll explain what this is. This is a common function for doing comparisons between two sets of things. So we have sets of tokens inside of our extracted data here. Jacquard's a great way to start to kind of compare what those sets look like. And it takes the intersection over the union so that you can kind of see how much overlap is there between these two sets. And we're going to set this threshold number. This threshold number is just going to be something where we say we're going to look for everything that has a Jacquard score at or above that threshold. And this is important because you don't want a lot of noise in your algorithm or it's going to take a really long time. A lot of these clustering algorithms and things like that really rely on the data being sparse. Like you want all the kind of useful sparse data that would come out, but you don't care as much about things like things that have very low similarity. And then generally, as I said, it's self-repairing, so even if you miss some good relationships, they should still appear. All right, so we can do a really naive thing here. We could do for sentence 1 in sentences, for sent 2 in sentences, and so on and so forth. This is going to be horrible. The end result of this is that we're going to take a very, very long time because with n squared of 70,000. What's that? It doesn't matter because I'm not going to run it. But yes. So the sentence 1, sentence 2. So if we went through and did this and we tried to do the Jacquard, so if we did right here, if we did Jacquard of sent 1 dot tokens and sent 2 dot tokens, this will do literally hundreds of millions of comparisons, and that's just not going to be realistic. So what we're going to do here is we're going to insert a little snippet, which is very useful, and I didn't want to talk about going through here, but it's an estimator. So on your spare time outside of this talk, I don't have time to go through it, but there's this thing called Minhashing. Minhashing estimates the Jacquard similarity between two sets. It's used a lot in document comparison to find a similar document. This will give us a much lower number of things we need to go over, and I encourage you to look up. I posted where the Wikipedia page on it and the data source, the library that implements this. So we're going to have this little library. We have Jacquard defined. We have this min-hashing. And we're going to insert some min-hashes for our 26,000 filtered sentences. Great, so now we have min-hashes for this, and now we need to actually do some edge generation. And unfortunately, for time's sake, I'm going to have to jump a little bit quickly through this. So we're going to mostly be copying over code and get to the data exploration, which is more interesting. So here we're going to kind of iterate through sentence 1, sentence 2. We're going to do query. We're going to do the index 1 equals index 2, and then we're going to run the Jacquard score. We're going to get above the threshold. We're going to add it to edges, and then we're just going to run this and populate a graph with a bunch of edges. So this runs pretty quick. We're going to run 26,000 of these. And apologies for the quickness, but we want to get to the interesting part. All right, and this is the clustering part. So I'm going to use a library that I implemented a few years ago. At the time, there was no good greedy agglomerative clustering algorithm. Heck, there wasn't even an agglomerative clustering algorithm that was good. Since then, there's been a few other sources. I think scikit or scikit-learn has a agglomerative clustering algorithm now, and there's a few other libraries that have them when I went back and looked. But this one's one I implemented, and we use at OpenGov. It'll work. Its kind of upper bound is 100 million edges. At 100 million edges, you start taking weeks to run instead of seconds or minutes. This should take, I think, 13 seconds to finish.
Is it built on network X? Or
It is built on, yes, it takes in a network X graph. Yeah, I'll explain a little bit. So you're going to take in a network X graph, and it will run the cluster and give you back an object that you can ask about the clusters. And you can specify, I want K clusters, or let it tell me. And it operates entirely on a network X graph. It builds another graph internally that has the whole dendrogram and then gives it back to you. And it's implemented, I posted the paper as well in the talk about how that's implemented and what it does. So we're going to go, let's go get some, I'm going to pop in these functions here, and then we're going to talk about them. So here we have this matplotlib. We're going to go and plot some things. First, we want to say for a big cluster of things, we want to know what's the central object in that cluster. So what's a sentence that represents that cluster? So we're going to iterate through and find the one that is closest to all the other things in the cluster. Similarly, we're going to take a score and score how similar are the things overall to each other. So we're going to run these two things, and we're going to get all the sentences clusters, and we're going to go ahead and sort them by the similarity score we have here. So we're going to get the clusters that have the most things that are similar to one another at the top. We're going to plot that, and then we're going to go grab only clusters who have between greater than 5 elements, and clusters who also have multiple sources. So we're going to plot this, and we're going to see this graph, which is nice. So the top is this there are 25 good clusters. They're between the size of 5 and 50 that have a pretty decent threshold for similarity. This means that if I wanted to print out one of these, so if I print out interesting cluster 1 or 0, print. So here you can see, here's an interesting cluster. It has budgeting, operating revenue totals from previous year. And you'll see in here there's a bunch of other things referring to budget, operating expenditures, and other things. So this is what a cluster kind of looks like. It's got 5 to 50 sentences in it. And so now we can kind of use this to judge, do we have clusters that are meaningful? If you have something between the kind of 0.3 to 0.8 range, those are things that could have value in them. If you're kind of outside that range, you're oftentimes going to end up in the boat where you don't really have something useful because either it's just the same term said over and over and over again, or it's actually a bunch of noise that got clustered because there's no really good clusters. You can see we'll do a little histogram here. So this is going to print out, you can see the size of our clusters. So they go all the way up to about 100. And then there's 10 good multi-source clusters that are fit within our filtered parameters. So we have 10 topics we've now pulled out of this data. And here's the histogram of the sizes so you can see it. And so now let's say we have these interesting clusters. So let's go ahead and print out a few. So let's print out maybe the 4th one. Great. So here it's going to talk about. You'll see if we grab out the centroid, we can do that as well. Great. So we have accounts for use of fund balance and balancing purposes. If you actually read through these, you'll see a lot of them talk about balancing and funds. They're all about accounts used to keep funds in balance and ensure that the right amount of money is in a fund. This is a really important topic in budget PDFs. It tells you, something about how the governments think about their budgets. And we just pulled this out by totally unsupervised technique. We populated out and popped out, hey, cluster 4 talks about this subject that we didn't even know existed before. But a domain expert would agree that, oh yes, this is a very important thing that budgets are trying to tell you. And we have lots of other clusters in here that do the same thing. So we'll have the sources of money, so intergovernmental and revenue sources, how they fund things. So what is the source of money that's funding things? Another thing a budget's trying to say, how is public money being allocated and used? And there's a bunch more of these, and if you download the example, you can kind of explore the data results we have here and see some of these. We do have some noise in here. You'll see there's these characters here, this sentence here doesn't look very good, and it looks like it's actually from multiple lines that kind of had the same terms grouped together. This is because our sentence parsing and our tokenizer wasn't very effective, and if we had gone back to the top and done a better sentence parser and kind of split those things up in a more informed manner, we would get much better results, and we would get more useful clusters. Another thing we also did, we're just using the words in the sentences. That's actually a pretty weak heuristic. It's really neat we can pull out topics just by words. The reality is if you want to really mine this and get something that you could get some real classes out of and get with more data, is you want to go back up to the top and kind of extract out word senses. You could do a better stemmer. You could go and look for what's the topics that you found in other domains with those words in them and pull them in all as features of your set that you're going to compare. Then you run the exact same algorithm. You have to change nothing in your algorithm but how you define the inputs of the things that you're Jacquarding. And all of a sudden you're going to get much, much better results. And we use this internally to intuit a lot of information about our labeled data and to extract out and identify classes of our data from any input from anywhere. And great, so I wanted to stop there, and I got through the code. Sorry, I had to paste a little bit more of it than I intended. But looks like we have 2 minutes for questions.
Thank you, Matthew. Thank you very much. We do have questions, but also people want to eat. So
Okay.
Are you available for question afterwards? I think it was really, really cool what you did there.
Thank you. Well, I'll be around, so I'll be here all day, and I'll try to stick around by this room for a little bit if people want to come up and ask questions.
Sure. Thank you very much. If somebody has a question right now, a short question, please. No? Okay. No, yes, I'll do text summarization. How would you give a summary for your talk? Hashtag for not data scientists, please.
Why would I summarize this talk? It'd be hashtag machine discovery.
Hashtag machine discovery, I can work with that. I'm in your audience asking uncomfortable questions. The system would break for non-English languages.
It would, but you could very easily either translate to stems that are in English, or you could even, and actually this system with stemmer, you could load a stemmer for a different language and run it on that.
Okay.
Additionally, you can also do, there's a lot of great sources for translating online. You can do rough translations, which actually work really well in this instance. So if you get a French document, you can actually, like Canadian documents, you could take it and you can translate it and put it through a translator, and you get a rough estimate, but you're already taking a rough estimate of the sentences anyway, so you only lose a little bit of quality.
What about Slavic languages?
What about what?
Slavic languages?
Slavic languages. I haven't got to dug into that, but I do know there are options for like BabelNet has a bunch of great other multilingual parsing capabilities, so you can pull out synsets that relate to English or other more established languages from languages that have less time focused on them.
Rule-based?
What's that? Rule-based? Yes, rule-based languages, that is something we are completely discounting in this process.
Oh.
We can, like, if you have rule-based languages, right, we're doing bags of words. So the order of the words in here we threw out. We also threw out, like, any semantic meaning of the stop words in the middle. So we lost some information there. We could recover that and get more results if we wanted to with more advanced techniques.
Noun identification.
For identification?
Noun identification.
Noun, yes, that's what, actually, if you look at WordNet is a great resource for that, though it hasn't been updated in a while, and I really wish somebody else would adopt that and kind of bring it up to the new, update the corpus. But that's a great resource. We use it internally for in determining whether a word has a noun sense, a verb sense, an adjective sense, all those type things. And you can use other tools like the Stanford NLP parser, which we've used as well, to try and extract out which one's the most likely candidate for a particular word in a sentence.
Do you want to expand it to other languages?
Yes, I think, and actually this will be a concern for us as we get more customers with other language data. We already have some French data, but it's also paired with the English language description, so we're okay there.
I want to sell you my corpus.
What's that?
I want to sell you my parallelized corpus, 22 language, 1 billion words.
That'd be wonderful.
Buying?
So yes, as we get into more countries, right now we're mostly focused in the US, but I mean, the rate we're going in a couple of years, that won't be true anymore, so yeah.
Thank you. Thank you very much.
Thank you.